This lesson is on exponential growth and decay. So exponential growth occurs when a quantity increases by the same rate r in each time period t. So there is a formula for exponential growth, and the formula is below here as follows. It's y equals a parenthesis 1 plus r, which is your rate, raised to the t power. T, again, is your period of time. So y represents your final amount. A is representing your original amount. R represents the rate of growth expressed as a decimal. And t is representing your time. So let's look at an example working with exponential growth. Here with example 1, it says a sculpture is increasing in value at a rate of 8% per year. And its value is, in 2000, was $1,200. Write an exponential growth function to model this situation, and then find the sculpture's value in 2006. So my 8% per year is my rate, my R. This is my R. And in the year 2000, it was $1,200. So $1,200 is going to be my A, my original amount. And then we're going to need to find out the time between 2000 and 2006 for my T. So the way to set this up is using the formula y equals a parenthesis 1 plus r raised to the t power. It's the same formula shown in the box here. We'll fill in the values given. So as we mentioned, my rate, r, is that 8%. We need to change that to a decimal of 0.08. Remember, move that decimal 2 places to the left to get percent to decimal. And then my original amount is 1,200. So it's 1,200 parenthesis 1 plus 0.08 raised to the 6th power. And when you solve that, this is what we get, 1,200, then 0.08 raised to the t power. So this is my function to model this. But then there's a second part of this, is to find the sculpture's value when in the year 2006. So what we have to do is we have to take 2000 and subtract 2006 from it. So we get 6 years. So using the formula, we have 1,200, 1 plus 0.08 raised to the 6th power. And when you solve that out, it's going to give you $1,904.25 for the value of the sculpture in 2006. You'll also see compound interest in this section, and that's interest earned or paid on both the principal and previous earned interest. There is a formula for compound interest. It's A equals P parenthesis 1 plus R divided by N raised to the N times T power. A represents the balance after T years. P is representing the principal, or your original amount is a way to put that. Principal would be your original amount. R is your rate. It's probably going to be seen in percent form. You would need to change it to decimal form. N is representing the number of times interest is compounded per year, and T is representing the time in years itself. So let's look at a compound interest example. It says write a compound interest function to model each situation. Then find the balance after the given number of years. So you have 1,200 invested at a rate of 3.5% compounded quarterly, and you have 4 years. So 1,200 is invested at a rate of 3.5% compounded quarterly. Quarterly is 4, and it's within 4 years. So step 1, we're going to use the formula and put these values in with the formula. So my P, my principal, my original amount is the 1,200. In the parentheses, we have 1 plus my rate. My rate is 3.5%. Changing that to a decimal is 0.035 over compounded quarterly, it's going to be over 4. And then that's raised to my 4 times t, and we're going to need to find my t, my time. So here's the formula set up with the values. When I simplify this, it's going to be 1200 times 1.00875 raised to the 4 times t power. So now we have to plug in the year t. Years is time. They're saying 4 years. So it's 4 times 4, which is going to be 16. So it's going to be 1200 times 1.00875 raised to the 16th power. And when we simplify that down, it's going to be $1,379.49. So the balance after the given amount of years, 4 years, is going to be $1,379.49. That's your answer working with compound interest. You'll also see what's called exponential decay, and this occurs when quantity decreases at the same rate r in a given amount of time t. So here's the formula, y equals a parenthesis 1 minus r raised to the t power. So notice this is 1 minus instead of 1 plus. Y again represents your final amount, a is your original amount, r is the rate of decay as a decimal, and t again is your time. Let's look at an example working with exponential decay. The fish population in a local stream is decreasing at a rate of 3% per year. The original population is 48,000. They want us to write an exponential decay function to model the situation and then find the population after 7 years. So step 1, we're going to use the exponential decay formula and plug these values into the formula. So A is going to be your original amount, the 48,000. Then 1 minus my rate is 3, but as a decimal that's going to be 0.03. And then my t time is 7 years. So what I have here is 48,000, 1 minus 0.03 is 0.97 raised to the t power. And again, they're talking about 7 years, so my time t is going to be 7, so plugging that into the formula. Now when you're plugging this into your calculator, you would do 0.97 raised to the 7th power, taking that and multiplying it by 48,000 to get approximately 38,783 people after 7 years. So the population after 7 years is approximately 38,783 people. The last concept we're going to talk about in this section is called half-life, and this is a common application of exponential decay, is working with half-life. Half-life is the half-life of a substance is the time it takes 1/2 of the substance to decay into another substance. So here's the formula. You have A equals P times 0.5 raised to the t power. So A represents the final amount. P is the original amount. And then T is going to represent the number of half-lives in a given period of time. So here we have cesium-137 has a half-life of 30 years. Find the amount of cesium-137 left from 100 milligram sample after 180 years. So we're going to use the formula. So we need to find out how many years this takes. So it's saying half-life of 30 years. In a 100 milligram sample with 180, we're going to divide 180 and 30 to get 6. So you take the time period by the half-life to get a value. T is 6. Then you use the equation. A equals P. My P is 100 milligrams times 0.5 raised to the 6th power, because that's the number of time, 6. When you simplify that down, you're going to get 1.5625, and that is going to be 1.625 milligrams of cesium-137 remains after 180 years. So that's the formula you use when working with half-life. You do need to divide the 2 years to get to get your value t, and then plugging that t value in with the rest of the equation to solve it.